Hi, I'm Dr. Memari, and I am performing the experiment 1 based on my lab manual at Central Campus. So if you're taking the course of 1045 lab at Broward College Central Campus, you will be using this video to obtain your data in order to complete the data sheet and to turn in for grade as an assignment. So I'm performing the experiment like you were here and performing the experiment. And so you be responsible for recording the data. And sometimes I want you to take like a screenshot of the data. So you need to read those numbers exactly the way it should be to collect the data. And without any other explanation, we're going to start the experiment. You have done at this point. You are done with the pre-lab assignments. You have read the experiment, the theory for the experiment. So we're just starting with the procedure for the experiment. The first part of the procedure, which is asking you to just going to follow the procedure to measure measuring mass directly. And the first item we want to measure the mass is measuring the mass of a penny. Measuring mass directly, you place the object, you make sure that balance is on. So you make sure balance is on, then you are going to, let's see if I can make sure to see for you to see it. So the balance is on. You press the pair button to make sure it's showing 0. And then you place your object on, which is the mass of the penny. Mass of the penny is 2.508 gram, and that's what you record as the mass of penny here. So make sure you record that the mass 2.508 gram. That's the mass of the penny. I only record the numbers, so you can't use just the chat area. You need to watch the video in order to make sense out of those numbers. Okay. Okay. A second, mass for 150 milliliter beaker. So if we have a beaker that is 150 milliliter, we are going to measure the mass, even though the line is going to this is the title. It goes up to 140, but this is the title 150. So we take the penny out and we place the beaker, record the mass for the beaker. So mass for beaker now is 65.550. Okay, that's the mass for beaker. So you record the mass for beaker as 65.550. And the unit is in gram. Based on the significant figures which you read in the introduction part, all the numbers shown in the balance, which shows the accuracy of this device, needs to be recorded. Then we take the beaker out. The next item to be measured is the mass of nickel, and we are going to measure mass of nickel. Same way, it has to be 0 first, then we place the nickel, and we record the mass for nickel. And it's 4.9. It keeps moving. The number is changing because it's sensitive, even sensitive to movement of my hand or talking here. So I have to make sure it's stable before I record the number. Okay, 4.955. 4.955, and that is the mass of the nickel, a nickel. Next, mass of a 100 milliliter graduate cylinder. So we take the 100 milliliter graduate cylinders. You probably noticed that all the objects that I'm placing directly on the balance stand, they are dry. They are not chemicals. These are clean and dry objects, so it doesn't damage the hand, the balance stand. The number is 119.285. 119.285. That would be the gram, 104 mass of 100 milliliter graduate cylinder. Okay, so this is for mass of the graduate cylinder. Next item to be measured is the mass of a watch glass. So we take that and we place a watch glass. Now, different watch glasses, they weigh differently. So like this one is about 30, the other one is about 48. The point of these practice is not to measure the mass and record those mass for calculation. The point is to practice enough using the balance. So for experiment 2 and on, whenever you are going to measure a mass, first of all, you have to decide right away, should you use mass directly, measuring mass directly, should you use mass by difference, or should you do the mass of the substance by indirect measurement. So it's just a practice for measuring and also recording numbers properly with proper number of significant figures, which shows the accuracy for your measuring device. Like this measuring device with this scale, it gives me 3 decimal places when I'm measuring the mass, and that 3 decimal place needs to be recorded when I'm measuring the numbers. So 48.110, that is the mass of the watch glass. Next, we are moving to mass of measuring mass part 2, measuring out substances. This is like indirect measurement. That is the time, for the time that we have chemicals, we are measuring chemicals. We cannot place the chemicals on the balance pan. So what we do first, we are going to place the weighing paper. Weighing paper is like a shiny paper, no pores, that when you put the chemical on, it would be in there and or be left when you're trying to transfer. So it should be inactive. Should not react with the chemical, and it also should be, so transferring would be easier. The weighing paper has the mass of 0.4. We don't need at this point because we are not doing by difference. We're just trying to use this as an indirect, so we're not putting the sample directly on the balance pan. So at this point, we are putting the balance at 0 again by pressing the tare button. So by pressing the tare button, I make it 0. Then add enough of the sodium chloride. I would add enough sodium chloride until it reaches to 2.75 exactly, because that's what I'm supposed to measure, 2.75 grams. So I would measure 2.75 grams of the sodium chloride indirectly using a watch glass. Just adding slowly, few crystals at a time, to make sure that it stops as close as 2.75. Okay. So I have 2.75 grams of sodium chloride, And then I'm going to measure. Next step of the procedure is to measure, and you are going to answer the questions in the data sheet. What is the question is asking you, like coming up with procedure? So basically you have to write in your own word, how did I measure this 2.75 gram using indirect measurement? Basically I placed the vein paper on the scale, press the tare button to make it 0, and when it is 0, they add enough of the sample to reach the point of the measurement, which is the 2.75 gram for that first compound. And second compound, I have calcium, is anhydrous calcium chloride. Anhydrous compounds, it means that they can absorb water. They are not hydrated, but they are good absorbent of moisture and water. And if you leave it out for a while, it's going to actually absorb the moisture from environment, lab environment, and it can gain mass. So when you are dealing with these compounds, when you are dealing with anhydrous, or anytime you see compound container with the anhydrous word on it, you want to make sure to close the container right away. And the reason you want to close the container right away is that you want to make sure the substance, the anhydrous substance, does not absorb moisture from the air, because if it does, then it becomes piece of rock. It doesn't serve the purpose, and the mass is not the mass of the substance anymore by itself. It's going to be the mass of a substance plus the water that it has been absorbed. So I measured the 5 gram. See, it fluctuates. It goes up and down because I'm talking, but that is the 5.00 gram of the calcium chloride. We're going to keep that for later on. If you gain water, how much water is going to be? So I'm going to save this sample right there. It will be sitting on the bench for me, and later on, after 15 minutes, we will measure it again to make sure if there is a change in volume or not. So it's 251 now. I will, if I remember exact, in 15 minutes, I will measure it again. We want to measure 22 grams of water, exactly 22 grams of water. So what should I do in order to measure 22 grams of water? First of all, I have to use a container. I cannot pour balance water on the balance pan. Definitely, that would be even silly to talk about. So we don't want to put any chemicals directly on the balance. So what we do, we just place a clean, dry beaker. Then you're going to add enough water to make it 25. So I'm going to press tare button again to make it 0, because I'm not measuring by difference, I'm measuring by indirectly. So it's 0 now, and I'm going to add enough water until it shows 22.00 grams, which would be about 20 milliliters. And now you can see that these numbers here, they are not very accurate because it shows about 30 milliliters, and that's too much. Okay, let me find a dropper, and I need to take some of the water out. Okay. It would have been smart if I put like 21 milliliters or 21 gram using the wash bottle that has deionized water sign on it, and then use the last 1 gram with the dropper, adding 1 drop at the time. It would probably make it easier and faster for me, so I didn't have to take the extra So you get to approximately to the you pour faster um, to get approximately to the number we needed, and then we add drop by drop until we get to exact number, which is 22.00. Okay, I have 22.00, and the last digit is impossible to fix it. So 22.00, take a screenshot of this number here. We're 22.00, and then or record the number. Okay. Good. 22.00. That is the mass of the water. There are two things. First of all, you want to make sure how to measure. If it's chemicals, it cannot be on the balance. Second, come up with a procedure that you can put exact amount of it. Next, measuring by difference. So we want to measure 50 milliliters of water in a graduate cylinder. So what you do first, you're going to make sure the balance is 0. So we use the tare to make it 0. Come on. 0, okay. We place the graduate cylinder that actually can hold up to 50 milliliters of water. Record this number, and that number is 119.2. It's changing, so I'm going to write the most stable one, 119.285, 285, 119.285 gram. This is the mass of empty. Mass of the empty graduate cylinder. Then I add 50 milliliters of water. I'm going to take it out, add 50 milliliters of water. So when I'm adding 50 milliliters, I go about 48 using the wash bottle, so I can add faster. Then the last milliliter, I learned already that it should be added with dropper slowly until the lowest point of the curve is at the 50 milliliter line. So it might seem like now it might seem 50, but if you're looking at the level, it's the level of the liquid is at your eye level, and you're looking at the meniscus or the bottom of the curve, it's not reaching 50 yet, so it needs like a couple more drops to reach to 50. So I'm going to add a couple more drops to make it the lowest point of the curve reaching 50, and record that number. That number now is 168.290 gram. It's the mass of graduated cylinder plus 50 milliliter water. Next, we want to measure 1, 2, 3 scoops of NaC in succession. What does it mean? It means that you place your vein paper, measure the mass, which is 0.4, 0.425 grams mass of paper, add 1 scoop, just going to give it 1 scoop, this, of salt, 4.941 gram mass of paper plus 1 scoop of salt. I add a second spoon. So this would give me mass of 2 scoops of the salt, whatever number is, and that is 9.255 gram mass of paper plus 2 scoops of salt. Next, as for 3 scoops, 13.706. So we measure the mass. The calcium chloride before and after it sits out on the lab bench for 15 minutes. So we have the mass before. The mass before was 5 grams for the calcium chloride. Now I'm going to measure again. That's like after. So it was 5 grams before. We're going to record that. It's the 5 gram calcium chloride before and measure the mass. Okay, if we have 2 more minutes before it gets to 15 minutes, I'm not going to measure it yet. I'm going to wait the 2 minutes because it's asking for 15 minutes. We can probably start with different part of the experiment. The second part of the experiment is measuring volume. For measuring volume, the devices that is used to measure volume, or we can at least talk about it, it's a graduate cylinder which comes in different sizes. 10 milliliter, 100 milliliter, 25 milliliter, different volume. There are lines and numbers, so you can read the level of the liquid. So if we have level of the liquid exactly at 50, we are looking for the lowest point of the curve, and if it's at 50, then we record that as a 50.0 with 1 decimal place, because the accuracy for this graduate cylinder is 1 plus minus 1. Now for this one is going to be plus minus 0.1. It's not plus minus 1, so it's plus minus 0.1, which is more accurate than the other one, than the 100 ml. So you have to actually make sure there's no bubble. There's a bubble here, so we have to wait for the bubble to break. Okay. Now we look at the meniscus. We are looking at the meniscus is the lowest point of the curve. You see the shape of the curve that the liquid stays in a cylinder shape equipment. The lowest point is what we are looking for. So if it falls between two lines, you have to kind of extrapolate that and record the number. You record properly. So it's not the if it's exactly on the line, it would be like a 0. But if it's between the two lines, you have to interpolate that. Interpolate, that means if it's like this one is 6.567, is between 6.7 and 6.8, then I have to interpolate, and if it's closer to 6.7, I would put like 6.7271. If it's closer to 6.78, then I would say 6.76, 6.78, depends on how close is to the top number. So that is called the interpolating the number to get the estimated last digit. Because the accuracy is a 0.1, the last digit is going to fall on the 100th place. So you're recording this number with 2 decimal place with the 10 ml graduate cylinder. Okay, we managed to get to the 15 milliliter, 15 minutes waiting time for the calcium chloride. So we're measuring the calcium chloride before, and it's the 5 point. The mass of the rain paper is not there. I have to get the mass of the rain paper out. Five point 212 grams after it sits out for 15 minutes. After it sits out and now next time measuring the volume. Basically the volumes are set. I'm going to take the computer to the other side of the lab so we can read these numbers. Here is the setup. The equipments are already set with the stations 1 through 5, and we follow the procedure. We are going to first read the numbers, and starting with station 1, which is the 10 ml graduate cylinder. 10 ml graduate cylinder. The amount of the water that is in here, basically just like reading what we had before, it's 9.567. Okay, this is exactly at 9.7, so it's going to be 9.70 milliliter. So that's the reading of the first graduate cylinder. Okay, 9.70 milliliter was the station 1. Okay, station 1. Station 2 is the 100 ml graduate cylinders, and we have 20. These are ones, so it's the 20, 21 is between 20 and 25. But since we have the small numbers, I can read the count those lines. 1, 2, 3, and 4. It's between 23 and 24. So to me, this is like in between 23 and 24 exactly. So I'm going to put 23.5. The last digit is the estimated digit. So 23.5 milliliter. This is going to be station 2. Station 3 is burette. Burette is more accurate than graduate cylinder. So it graduated from 0 on top and 50 milliliter all the way down here. The numbers are shown, and between the numbers you have the line. Each line shows 0.1. So since each line shows 0.1, you can interpolate and get the second decimal place out of measuring burette or volume with the burette also. When you measure the volume of burette, you're not saying how much liquid you have in here. You're just saying this liquid is across which number. So basically it's called burette reading, is not called volume. So burette reading, right now, it would be easier if you place a colored paper or white paper behind it. You see, it's much easier to see. That's why sometimes we use paper behind the line, so you could see that meniscus or the lowest point. And the lowest point here now is 26.123. It's not reaching 4, but it's very close to 4. So 26 point. Okay, I'm reading from the top. So 25, you read from the top to bottom. So it's between 25 and 26. So it's going to be 25. You go down. So for burette, you have to look from, because the numbers is increasing up, down, as I said. So it's 25.5.6, but it's very close to 0.6. So it's going to be between 0.6 and 0.7. So it's very close to 0.6. So it's going to be 6.2 in my estimation. Okay, so 25.62. Okay. There are again two numbers that shows how much liquid you have in the beaker. This is like how much you dispense it out. So it's starting from 0. Obviously, if it's filled up to this point, it's not zero volume. It's not helping much. So you have 0 number here, 0, and then you have 0 when there's nothing in here. When you are reading to find out how much liquid you have to read from the side that is increasing down, up. And then you have to interpolate the number, basically. So it's between 100 and 125, because you have the 150. There is a line in between the two. So it would be 100, and this is 125. So to me, it's not exactly in between. If it was exactly in between, it would be 100 and like 12.5. So to me, it's like 110 milliliter at this point. So 110, about 110. That is the station 4. Station 5, same thing for the flask. The numbers showing here is between 50 and 75, that's 100. Obviously, this number is between 50 and 75, and we have to have our best judgment and the estimation how much this is going to be. So it's approximate number. That's why it's not accurate. Even though you have those lines, but burette and flask, they have different purposes in the lab. They are not to measure exact numbers. So this is about 65, 65 milliliter, station 5. 65 milliliter about station 5. Okay, part 2-2, determine the volume of a test tube. To determine volume of test tube, we take a test tube and we fill up the test tube with water and see how much is going to hold. So this is the test tube. It's not a perfect cylinder, so we can't measure the height and the area to find the volume by calculation. So in order to find out how much is going to hold, how much water is going to hold, we can fill it up exactly to, there are two ways we can do. We can use the 100 ml of water. We can fill up the graduate cylinder to 100 exactly. And I learned my lesson. I have to adjust the top to reach to the exact volume using a dropper. So I have 100 milliliter almost. I have 100 milliliter of water in graduate cylinder. Now, I transfer water to carefully without spilling any water out. If I transfer enough to fill up this test tube with exactly to the top, like completely filled up to the top. Okay, filled up. How much water did I use? How much water did I use for this? Is I started with 100 and I end up with 40.5. So 100.0 minus 40.5, that equals volume for test tube. Whatever number you find there, that would be the volume for test. Next, we want to measure the volume for golf ball. To measure the volume for golf ball, if I use displacement, that means, which I've seen some of students using this, you put water in a beaker and then you add the golf ball into it. The level goes up by displacement to you read it. Beaker is not a good device to measure volume, so it's not going to measure accurate volume. So you're going to have lots of error in this. The better way is to find the diameter for the golf ball. When you have the diameter, you divide by 2. You get the radius for the golf ball. And when you have the radius, then you would use the formula for volume, the 4 over 3 fraction pi r cubed. Then you are going to use the formula in order to So all you need for this part 3, part 2-3, it's the diameter for golf ball. So diameter for golf ball, I have to make sure that it's perpendicular, because it's again hard to get the exact height because it's round. So I'm going to make it touching. I'm going to use the centimeter side. Okay, so you could also see it. I have the golf ball, and I use 2 rulers perpendicular. See, this is touching the top. This is touching the top. This ruler is touching the top of the golf ball, and the bottom of the golf ball and the ruler is sitting on the cart. So if I just find out what this number is, which is 3.8 centimeter, so 3.8 centimeter, 3.80 centimeter, that's the equals to 2R for golf ball. And when you read the experiment, then you understand what is that 2R means, and you are going to find them. 20 pieces of zinc metal. 20 pieces of zinc metal. We find the zinc metal first, and we measure the volume for zinc metal. Here's the zinc metal. In order to measure the volume for zinc metal, see, it's irregular shape. Any irregular shape solid, you cannot find the dimensions and use a formula just like you did in math to find the volume. So because it's irregular shape, what we are going to do, we are going to count first 20 pieces of this 2, 5, 9, 10, 11, 14, 16, and 20. I have 20 pieces. Then I'm going to take a graduate cylinder, make sure that these pieces fit into this, because if they don't fit, it's not good. If they are small enough to fit in 10 milliliter graduate cylinder, it's better. But if my pieces are large, I cannot use the 10, I have to use the 100. Place some water in there already in the graduate cylinder. Read this volume. So that volume is 6.75. 6.75. You have in the data sheet to make sure that you have proper numbers. So this is for part 2. Six 6.76 milliliter is the volume before adding zinc. Then I add the pieces of zinc into the graduate cylinder carefully. The volume now, it goes up So this method is called measuring volume by displacement. When I add the zinc, it displaces the water. Water goes up. I read the number again. 8.35 and 8.35 is the volume after adding zinc. They can find the volume of the zinc. That's for 20 pieces. If you divide by 20, you get the volume for 1. Volume for air inside a rectangular box. You're going to measure the dimensions. So the dimensions that are measured here, I'm going to use the centimeter from one end to the other. So this is going to be 14.50. 14.50. The length is 21.2 times 8.8. Density of the solid. We want to measure the density. We don't measure the density. We basically calculate the density, but in order to get the calculation or the value for density, we need the volume and we need the mass. We already have the volume. You can calculate the volume for the golf ball. And now I'm going to give you the mass for golf ball. For the 6.138 gram. So for the 6.138 gram is the mass for the golf ball. You already have the diameter, so you can get the radius and find the volume for the golf ball. Then you can calculate the density. Next is irregular shaped solid. The irregular shaped solid that we are going to use is going to be the cylinder shape. This is metal. It's not a perfect cylinder. There is something coming up here. What we do, we are, because just like zinc, we are going to find the volume by displacement. But if I use the volume first, if I find the volume first, it's going to get wet. And if it does get wet, then it's going to have different mass than a dry sample. So I have to find the mass first. So every time you're measuring mass and volume for the same object, if it's solid, measure the mass first. It's a heavy metal there. The mass is 63.397. Then we get the volume. Read the volume here is 40.3 to me. Then we place the object we have to be very gentle and carefully slide it down. And read the volume again. Is it 40.95? Then it would be 40.95. Sorry, 49.5. 49.5 minus 40.3 equals whatever number you find there is going to be milliliter volume of solid. The volume for the solid. You also want to find the density for water. To find density for water, we take 10 milliliters of water. We're going to use the mass of graduate cylinder. Okay, we're going to get the mass of graduate cylinder. Because in order to find density for water, we need the mass for water and we need the volume for water. To get the mass for water, I have to find, so now you practiced already, you have to measure the mass. How do you measure the mass for water? You have to have an empty container. You measure the mass of the empty container. And then you are going to measure the volume. So you add the 10 milliliter. Then you measure the mass again. That would be the mass of the container plus the mass of water. Let me record this number so I could put the number in one step for you. Get a pen to record that. So I have a 37.862. Then I add 10 milliliters of water. I pour fast with the wash bottle and then adjust the last drops with the dropper. The 10 milliliters. Now we get the mass again. $47.855 minus 37.86, right? 862, that's what we had before. This is going to be mass for 10 milliliters of water. So if you only look at those numbers, the numbers are not going to make sense. But when you watch the video and you look at the numbers, then you can see the actual value for the numbers. What does it mean? So how did we come up with the 47.855 and then 37.862? What are those numbers? The 37.862 was the mass for empty graduate cylinder, and the other one was the mass for graduate cylinder plus the water. Okay, next step on the procedure is asking to measure the density for unknown liquid. So we already have the mass for graduate cylinder. We're going to put the unknown liquid. I'm just going to pick one unknown liquid. We keep the unknown liquids inside the fume hood, so it's not there. Let's look for unknown liquid. And why fume hood? This is the fume hood. It's a small room. The fan is on. Any vapor of this chemical is going to be pulled up, filtered, clean air would come back to the room. So especially chemicals that they have low boiling point or they are volatile or organic compounds, it's not safe to keep it outside. We have to place them inside the fume hood. So we get 10 milliliters of this sample. Exactly 10. We measure the mass on the scale. Okay. This one now is 45.20. That's the number that is going to be recorded. That's what we have. I'm going to wait for the most stable number because it's fluctuating. Okay, 45.815. 45.815 minus the empty graduate cylinder was 37.862, and based on this we can find this is going to be in grams mass for unknown liquid. For 10 milliliter of unknown liquid. So if you have the mass, you have the volume, we can calculate the density. I'm going to place it back in the fume hood so I don't have to inhale the chemical. That was unknown A because it's going to ask you which unknown you are using. Last step for the experiment is to find the boiling point of an unknown liquid. What is boiling point? Boiling point is the temperature that liquid changes to gas. We have to set up the equipment to measure the boiling point. The picture is showing, the last page of the experiment is showing you how to measure the boiling point. So we're going to start with the hot water, heating up water for the boiling point. This water is a lot, so probably be safe to use a small amount of water. Maybe it takes less time to heat up. Okay, we have the water boiling. We are going to use a thermometer. Use a thermometer clamp to hold the thermometer. Okay. So we are going to use the thermometer clamp, and the sample is going to be placed in seal tube. These are like small, tiny test tubes. Going to attach it to the thermometer. Keep it at the level of the thermometer, like this, the thermometer bulb, and let me seal it first. So you're going to use a rubber band to hold the two together. We place the liquid unknown into the seal tube and use a capillary tube with open end down. Here's the capillary tube with the open end, closed end. We place the capillary tube with open end down. The liquid goes inside the seal tube. Liquid would be inside the seal tube. So I'm going to add the few drops of the unknown A. I'm using unknown A for boiling point also. And I'll be right back. Okay, so I'm just going to the fume hood to get few drops. I place in the seal tube and I place the capillary tube with open end down. Then I start heating up. When the temperature reaches boiling point of the sample, what's going to happen, you will see you would see the bubbles coming out of the capillary tube, because if the liquid boils, the liquid inside the capillary tube is going to boil also. And since the closed end is on top and is closed, obviously, the vapor cannot go out from the top of the capillary tube. The vapor is going to go out from the bottom side of the capillary tube, which is open, into the liquid. Then we see those bubbles coming out. That's the time that the liquid starts boiling. And we can stop the boiling. We can remove this, but since the hot plate is hot, if I turn it off, still is going to be hot. The better practice, if I was using Bunsen burner, if the gas was on, if I was using Bunsen burner, I turn off the Bunsen burner and I wait for the bubbles to stop boiling. And before the liquid goes back into capillary tube, it's going to be the exact boiling point. But the boiling point that I'm recording at this point using is going to be still accurate, but plus minus like 1 degree Celsius, which is still a good piece of information to identify a compound. This is a density is a physical property for a compound. Same thing for boiling point. And the color and the odor, all of that, it can help me to identify what is my compound. For example, if I know my unknown boils at 78.5, then I know most likely that compound is not water, because water boil at 100 degrees Celsius. If I know the density of the substance is very close, very, very close to 1 gram per milliliter, and the literature value for density of water is 1 gram per milliliter, then most likely that unknown is water. If the unknown boils at 100 degrees Celsius, same thing. That means that you have your unknown is water because it's boiling at 100 degrees Celsius. So let me bring the sample, place it in here before it gets too hot, because I don't want the temperature of solution to be higher than temperature of the sample, boiling point for sample, because as soon as I place it, it starts boiling and I don't get data. So I better move fast to get the sample. Okay, I added like about 5 to 6 drops of this liquid into the seal tube, and it's much easier to see the bubbles coming out into the liquid. And I'm going to place it in the secure it with the thermometer and place it in hot water bath at this point. The liquid should be inside the water. The sample, the unknown sample, should be inside the. Okay. Now all we have to do is just wait and look for the bubbles coming out. If the temperature is high, it might happen quickly. So I'm going to sure it's not too high. The temperature of the water before you put your sample, it must be lower than the boiling point of your unknown. Otherwise, as soon as you place it, it's going to start boiling. I'm just waiting. Really, this is not, just want to make sure both thermometers are showing the same number. Because if your thermometer is not showing the right number, you're not going to get the right answer. Okay, it looks that my thermometer is working and it's showing the same number as the other thermometer. So we just wait until we see the bubbles. And that is the last part of this experiment. I hope you have all your data to finish your data sheet to turn in as assignment for the course, especially for the remote learning. The book, the lab manual that you're getting, lab manual, it's going to be ebook for easier use, and it's going to be, you need to order from Vital Source. You should get the information in as an announcement or in your syllabus, how to order the book. I'm removing the bubbles that are coming from water, from the capillary tube, so you could see the bubbles coming out as the sample is boiling. Okay. You might see now, like one bubble comes out, like one at a time, but I'm looking for the study bubbles coming out. It's very close though. Now we're getting, so do you see those bubbles? Hopefully you see those bubbles. And if not, you have to trust me. Those bubbles are now coming out of the capillary tube. See that continuous bubbles coming out of the capillary tube, and I'm recording that number as 64. So 64 would be the boiling point. You just need to know how to record and how to perform and how to set up to I'm just holding the camera closer so you could see those bubbles coming out. And when I was talking about the liquid inside the capillary changing to gas and bubbling. Unknown is A. I'm going to stop recording at this point. You have all your data. You're responsible for the data sheet to be turned in. Very good. And thank you.